2, differentiation exercise. So here we need to find the coordinates of the stationary point and determine their nature. So we have A, where y equals x cubed minus 3x. So the important thing to remember at first is that the stationary points are at dy by dx equals 0. So we need to find dy by dx, multiply by the power and reduce the power by 1, and then do the same for the other term. And we're looking for where that is equal to 0. So that's the same as where x squared minus 1 equals 0. And when we factorise this, we get x plus 1, x minus 1. So either x equals minus 1 or x equals 1. So now we need to find the y values at these x points. So that would give us, if we substitute minus 1 into the original equation, we'll get minus 1 plus 3, which would give us a y value of 2. And if we substitute x equals 1, that would give us 1 minus 3, which would give us a y value of minus 2. So we've got our two stationary points, and we need to determine the nature at either side of these points. So we'll test the left-hand side of x equals minus 1, which would be x equals minus 1.1. So substituting that into this equation here, we would get 3 lots of minus 1.1 squared minus 3, which would give us a gradient of 0.63. And now having a look at the right hand side of x equals minus 1, which would be the point x equals minus 0.9. So that would be 3 lots of minus 0.9 squared minus 3, which would give us a gradient of minus 0.57. So because we go from a positive gradient to a negative gradient, that means the point minus 1, 2 is a maximum. And now we need to test the other point. So we need to test the left-hand side of x equals 1, again substituting it into 3x squared minus 3. So that would be the x value of 0.9. So 3 lots of 0.9 squared minus 3 equals minus 0.57. And then we need to test the right-hand side of x equals 1, which is the x value of 1.1, which is 3 lots of 1.1 squared minus 3, which would give us a gradient of 0.63. So that means that the point 1 minus 2, because we go from a negative gradient to a positive gradient, is a minimum. And again, you don't have to draw this on a graph, but I'm just going to show you what a quick sketch would look like. So the graph would cut through the origin because the original equation doesn't have a plus or minus on the end. And our turning points would be at minus 1, 2. That's where our maximum is. And our other turning point would be at 1, minus 2, because that's where our minimum is. So again, you don't have to draw the graph, but I've just done it to show you what a sketch would look like. Moving on to B now. So for B, we have y equals 12 minus x cubed. So again, the first thing to do here is to differentiate. So dy by dx equals minus 3x squared. And remember again that the stationary points are at where dy by dx equals 0. So we want minus 3x squared equal to 0. Well, that's just the same as x squared being equal to 0, which is x equals 0. And when x equals 0, we have a y value of 12, just by substituting it back into the original equation. So we have our point, now we need to determine the nature of it. So we need to test the left-hand side of x equals 0, which would be x equals minus 0.1. So substituting that into minus 3x squared will give us a gradient of minus 3 lots of minus 0.1 squared, which gives us a gradient of minus 0.03. And now we need to test the right-hand side of x equals 0, which would be the point x equals 0.1. So that's minus 3 lots of 0.1 squared, which would be equal to minus 0.03. So our point 0.12 is a point of inflection, which you would expect because we've got x squared equals 0 here, which means that it's a repeated root. So I'm just going to show you what this would look like. Again, you don't have to draw the graph. I'm just doing it to show you. So at the point 0.12, sorry, that graph's wrong. So at the point 0.12, we have this point of inflection. So moving on to part C now, we have y equals 4x cubed minus x to the power of 4. So again, we're looking for where dy by dx equals 0, so we need to find what dy by dx is. So multiply by the power and reduce the power by 1 gives us 12x squared minus 4x cubed. So we're looking for 12x squared minus 4x cubed equals 0. So that's the same as 3x squared minus x cubed equals 0. And if we take x squared out, that'll give us 3 minus x equals 0. So x equals 0 or x equals 3. So when x equals 0, we end up with y equals 0 for our y value by substituting it back into the original equation. And when x equals 3, we end up with 4 lots of 3 cubed minus 3 to the power of 4, which gives us the y value 27. So now we need to determine the nature of each of these turning stationary points. So we need to test the left-hand side of x equals 0. So that would be x equals minus 0.1. And that would give us, substituting that into this equation here, that's 12 lots of minus 0.1 squared minus 4 lots of minus 0.1 cubed, which gives us a gradient of 0.124. And now testing the right hand side of x equals 0, which is x equals 0.1, that gives us 12 lots of 0.1 squared minus 4 lots of 0.1 cubed, and that gives us a gradient of 0.116. So as you would expect from a double root, the point 0, 0 is a point of inflection. And now we need to test the other point stationary point that we have found. So we need to look at the left-hand side of x equals 3, which would be x equals 2.9. So 12 lots of 2.9 squared minus 4 lots of 2.9 cubed, that's substituting 2.9 into the gradient. That gives us a gradient of 3.364. And now we need to test the right hand side. So the right hand side of x equals 3, that will be at x equals 3.1. So that's 12 lots of 3.1 squared minus 4 lots of 3.1 cubed. And that comes out with giving us a gradient of minus 3.844. So because we go from a positive gradient to a negative gradient, we know that the point 327 is a maximum. So again, I'm going to draw you a quick sketch, but you don't have to because it doesn't ask for one in the question. So at 0, 0, we have our point of inflection, and at 3, 27, we have our maximum. So again, you don't have to draw any of these curves. I've just done it to show you what they will look like.